Here we are at 2.2 land, intramolecular force and potential energy. So if you look at this word intramolecular, please note that that is not intermolecular forces. That will come later. This is intramolecular forces, so this means within. So these are the forces within one molecule, and potential energy. So has to do with atoms and ions, representing relationships between potential energy and distance between atoms based on factors that influence the interaction strength. So it's all about the strength of the chemical bonds inside molecules. Okay, here's a graph of potential energy versus the distance between atoms. Basically, there is a distance between two atoms in a chemical bond that is the ideal bond distance because it's called an energy well. So it's basically the lowest point in energy. Remember that everything in the universe is trying to get to be as low energy as possible. That's why things fall, because when they're on the ground, they have lower potential energy than when they are up high. So if we look at this graph down here, you just need to be aware of it and know what it's saying. We have two hydrogen atoms bonded together, and this is the ideal bond length at 74 picometers, really, really tiny meters. So if you get longer than 74 picometers, then they're too far apart and this bond will break. If the bond length is too close together, the nucleuses will get too close together, and both nucleuses are positively charged, so they will repel each other. So basically, since anything above absolute zero is moving, this is always going to be moving, the bond is a little bit squishy. It's going to extend and contract and go back and forth a little bit. So basically, the energy is kind of just wobbling back and forth here, and that's why it's called an energy well, because it just stays basically at the bottom of the well. Theoretically, if you give it enough energy, it'll do that, and then it will break the bond. That happens a lot. And if you give it too much energy this way, you'd have to figure out how to squish it together. That's not really possible. And if you notice, the energy increase is much steeper and quicker to go that way than this way, because eventually there's no attractive force between the two nucleuses anymore. So that's basically all this learning target is to just know that there is a preferred distance of two nucleuses in a chemical bond, because if they're too far apart, that bond breaks. If they're too close together, the positive nucleuses will push them back apart. Okay, this one says in a covalent bond, the bond length is influenced by both the size of the atom's core. So basically, bigger atoms are going to have a larger bond length because, they're bigger. Smaller atoms are able to fit closer together. So the size of the atom's core and the bond order. So bond order is how many bonds they have. So this is first bond order, second bond order, third bond order, single bond, double bond, triple bond, etc. Bonds with higher order are shorter and have larger bond energies. So if we think about this, triple bond versus that single bond, this triple bond has 3 times the electrons. It's got 6 electrons versus 2. And these are going to be closer together because if we actually looked at the geometries of bonding, it's something called bond symmetries. They basically have to be closer in order for those bonds to form. You can also think about it as an analogy of rubber bands. So if you have 3 rubber bands around something, they're going to be held much more tightly together and harder to separate versus just having 1 rubber band around them. So I do believe that that's all that one says. And then there's one more. Basically, we can use Coulomb's law when we're talking about ionic compounds. So these past 2 were only about covalent compounds. So hydrogen and hydrogen, 2 nonmetals. Carbon, carbon, 2 nonmetals. When we talk about ionic compounds, it's no longer just one molecule. You have to consider the entire 3-dimensional crystal structure, because sodium chloride is not the interaction between one sodium ion, and one chloride ion, because since this is positively charged, and since chloride is only on one side of it, it basically leaves all the other sides available for other negative particles to be attracted to it. And then since these are 2 negatives next to each other, you can fit a positive in there, and then it just alternates charges like this. But if we think about this 3-dimensionally, this sodium atom, you could also place 1 chloride ion there and then 1 chloride ion behind the board. So in reality, each ion in the sodium chloride crystal structure is actually interacting with 6 other ions. So it is much more than just the interaction between one ion and another ion. It's an interaction of the entire crystal structure. The crystal structure is called a lattice. It's a crystal lattice, so it's called lattice energy. So it's basically the energy contained in the three-dimensional structure. So this is very, very similar to what we did in Unit 1 with figuring out periodic trends. We're going to use Coulomb's law again. And basically, the stronger the attractive force, so remember that's effective nuclear charge and the size of the atom. So the same thing applies here, except instead of effective nuclear charge, we're just going to literally use the charge of the atom. So sodium is +1. So if we make a crystal lattice out of calcium, that would theoretically have a higher lattice energy because since it's +2, it should theoretically have twice the attractive force, which would double the lattice energy. Of course, it's way more complicated than that, but in general, the higher the charge, the more the lattice energy. So the more attractive the ions, the larger the charge, smaller radius, the higher the lattice energy. And that's pretty much it. Usually when they do lattice energy, they will show you pictures of the lattices, but that's not terribly important. The only things you really have to look at are how positive the charge is, not the nucleus, the charge of the whole ion, and then how large the radius is. And I do think that's it for 2.2.